about the formal description of a DFA, and I will refresh our memory a bit. A DFA is something that looks like this. It is a tuple in 5 parts, and the parts we typically write this way: Q, sigma, delta, Q0, and F. What these mean: Q, this is the set of states. Sigma is the alphabet, which is also a set. Delta is the transition function, which is kind of the most complicated ingredient here. This Q0 is the starting state, and the F is the set of accepting states. All right. What I would like to do today is go through the various other concepts that we've talked about related to DFAs and try to express them in this kind of formalized language. I am referring to concepts like, what does it mean to accept or reject a string? Can you write that in terms of this symbology here? Or what does it mean, the definition of the language of a DFA is the set of all accepted strings. I want to see if we can write a definition for that set in terms of the more abstract formal description of a DFA. Remember how this delta works, just because that's the most complicated part. The delta is a function, and its domain is Q cross sigma, and its codomain is Q again. What that means is the stuff you plug into delta looks like a pair, where you have one state followed by an alphabet letter, and then the answer that you get is a state. And so a typical, typical application of delta would look something like delta of Q comma A equals R. So if you see that, delta of Q comma A equals R, what that means in terms of the diagram, this means there is an arrow like this where there's some state called Q and some other state called R with an A on it, right? That's the meaning of this transition function, this delta. Okay? Or another way you could say what this means, just in plain words, it means if we are in state Q and we read A, then go to state R, right? That's another way to say what that means in ordinary words. All right. In order to discuss the other things that I said we wanted to get to today, actually there's a variation of delta that is a little more useful, or more I don't know, I guess more useful? I don't know. There is also, I'll just say, there's also what we call the extended transition function. And it is written delta star, and it's also a function. It has a slightly different domain. The domain is Q cross sigma star going to Q. Remember the other one, its domain was Q cross sigma, right? That was the other one. The difference here is that this part consists of any strings that is not just a single letter. Right? Not just a single letter. But you can put any string in that case. But then otherwise it does the same idea. Sorry, I'm off the frame. Out the frame. Off the chain. It's the same idea where it's just a function which tells you if you start in a particular state, but this time if you do a whole string, where is the state that you end up in? So like, for example, in our previous, say the one on the quiz was like this. So if I were to, I didn't do this on the quiz, but if I gave the states names in this case, let's call them S and T are the names of the states. So here I would say, For example, delta of S and B equals T. That means if I'm in state S and I do the letter B, I end up in state T, right? But that's the ordinary delta. You can also talk about what we call the delta star, the extended transition function. It works like this. What is delta star of, let's say, S, A, B, A? It's the same idea, but you're just putting a whole string in there rather than a single letter. So this still means if I start in this state S, and then I do ABA, what's the state I end up in? And what would you say? You just got to follow the arrows. What do you think?
T.
I think T. Yeah, if you start in S and you do A, then B, then A, you end up in T. All right? This is the delta star. It just does a whole string at once. So what that means is if we start in S, I'll just write this in words again, and we read the whole string, ABA, then we end up in T. That's the meaning of the extended transition function. All right. All right. There are some basic properties of delta star. Delta by itself can be any function, and you really there's not much that you can say about delta by itself because it could be anything. Delta star, though, there are some properties that delta star will always have. So here's, I will say, simple properties of this function, delta star. And as soon as I write them down, you should be able to say, what if I put the empty string there? You know, the ordinary delta, you are not allowed to put empty string in that position because the ordinary delta, you must be an alphabet letter that goes in the second part of the pair there. But the delta star can use any string, and so you could put the empty string. Anybody want to say? This is true, not just of that example up there. I'm just talking about in general, no matter what the DFA is. Don't look at that particular diagram. You just have to imagine. What if, what the meaning of this, remember, is if I start in state S and then I do the empty string, what state should I end up in? What do you say?
S.
S, yeah, that's the only thing that makes any sense to say here. If you start in state S and you don't do nothing, that's what it means to read the empty string, then you end up in state S still. So I put still S. Simple properties of delta star, all right? This will always be true, no matter what the DFA looks like. This will always be true. Okay, another simple property. If the length of S equals 1, so X is just a single letter, then delta star of S and X is the same as the regular delta, right? In that case, then they mean the same thing. The delta star, it also just tells you where does the thing go if you do X. And if X is just a single letter, that's the same as the ordinary delta function. All right? And then one last simple property. This one is a little less clear, but here it is. Delta star of S and xy. What if I have a string followed by another string in that position, x and then y? Now, I would like to say something about what the answer of that is. And I'm going to write something. Don't write this down because this is not correct, what I'm about to write. But this is just to get us thinking. The idea here, something like that, like when you start somewhere and then you do x followed by y, it should be something like starting there and doing x and then doing y after that, right? This is the idea here. This, though, what I wrote over here doesn't really make sense, though, because I just wrote these two things next to each other as if they're like multiplied together or something, but the answer of this delta is a state. And the answer of this delta is a state. And so it doesn't make sense to write two states next to each other as if they were multiplied. So this is not correct, but I'm trying to get at the idea. If you do x and then y, there should be another way to write that as doing x first followed by doing y. Anybody have any ideas about this?
Would you like put a delta inside a delta except in like the state position?
Mm-hmm. I hear that. It's kind of like this thing. See, the problem with writing it like I did and then crossed out is these answers are both states, and you can't just write one state times another state. But you should feel like maybe I could plug this state inside where the state goes in the other one. And that actually is exactly what it should say. So the correct formula here, I'll just copy this down again. So we've got it in one line. Delta star of Sx, comma, y, like that. This looks pretty weird, but what it means is first you start in state S and you do x, and you end up wherever you end up, and then continuing from there, if you do y, then you get to delta star of S and xy. All right, so that's a strange one, but I hope it makes sense. Delta inside a delta. That's the way it's got to be. All right. Any thoughts about this? So this is the extended transition function. It comes up in these formal descriptions from time to time. All right. Okay, I think we are ready to give a real definition for one of the concepts that we've been talking about all along. Okay, so here's a real definition. I'm going to say what it means for a string to be accepted by the DFA. Of course, on the diagram, it means something informal, like if you start here and you go jumpy, 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 then eventually you get to the accepting state. You want to say this in more, more formalized language. So I will say, given a DFA M, which is written as, Q sigma delta Q0 and F, and also a string X in sigma star. Remember, sigma star just means the set of all strings using letters from sigma. Then we say that M, well, I'll say it the other way around. X is accepted by M. This is what I'm defining. This is the definition of what it means to be accepted. X is accepted by M when, informally speaking, it means when, if you start in the starting state and you do X, it ends in an accepting state. Anyone want to try and write that out in this formal language here? How about someone I haven't heard from today? You can actually write this in a very sort of compact way, but whatever I put here, what it's going to mean is if we start in the start state and do X, then we end in an accepting state. Anyone want to try to translate that into our formal language? You can just do a piece of it if you want. Nobody's saying anything. How about this? I'll give you a hint. Should be a delta star in here. And if there is a delta star in here, it better have two things in there. Delta star, remember, means if you start somewhere and you do something, right? Like what you put here is the starting state, or this is wherever you're starting, and then this is the string which you're actually reading. What do you think? What should I put in those two parts, just to translate the words down there?
I can answer, but I've talked before, so I don't know if you want me to.
Give me somebody else. I do appreciate.
Okay.
Would it be S1X?
Yes, X over here. And in the first position, I think what you want is the starting state. Is that what you meant when you said S1?
Yeah.
Yes. So according to my description up here, the starting state has a name, and it's this one, Q0, right? when you write the definition of the DFA, that's what Q0 refers to. This is the name of the starting state. So that's what I put right there. All right. So this says, as written, this means what it means the state that you end up in if you start in the starting state and you do X. And what do I want to say about that? I'm trying to define what it means for X to be accepted.
If like that equals a state in F.
Yes, if this is one of the elements of F. Actually, there's a very simple way to write that, and it's like this. Right? If that is an element of F. So all these little words down here, they are expressed very simply by saying this. The transition function, the extended transition function, if you start in the starting state and you do that string X, it ends up being an element of this F, which is the set of accepting states. All right? It's kind of cute that all those words can be boiled down into this, you know, super compact set theory notation. I kind of like that. All right. Any questions about that? Any thoughts? Excellent. Okay, I think immediately then we can define what the language of a DFA is, right? So let's give another definition. For a DFA, you know, M equals, all right, it's just going to be all the same stuff again. The language of the DFA is, so this is the definition, the thing that I'm defining. The language is, we write L of M. It's just the set of all X's which are accepted. So I'm going to say the set of all X in sigma star, that is, X has to be a string using the appropriate alphabet, which is sigma, such that, and then what I put to the right of the bar is just going to say X is accepted by M, but I'm not going to write those words. I'm going to write this because that's what X is accepted by M means. So to the right of the bar, I put that stuff. Delta star Q0X is in F. All right. This is what the language of the DFA is as a set. It looks very complicated when you write it that way. But there's power in those little symbols, right? Every little part of that carries a lot of meaning. This is the official definition of the language of a DFA. All right.
Professor, do you mind just saying what sigma? No, not sigma. The big thing E, like what looks like an E, is that sigma?
Yes, that's a capital sigma. Yeah, that's
what's
the.
sigma star mean again?
So sigma itself is the alphabet, which is usually just like A comma B or something like that. Sigma star means all strings from that alphabet, which would be any string of A's and B's or whatever it is. So sigma star is an infinite set, much bigger. Sigma is just a few different letters. Thank you for the question.
Can
Another
you just
question.
say what the whole thing like reads when you read it in words?
Yeah, so this says the language of the DFA is, first of all, it's all X's, which are strings. That's what this says. Such that, and then this business over here, I just copied the same thing that I wrote up here. And so that means that if we start in the starting state and we read the string X, then we end in one of the accepting states. Right. And then one last simple definition. Now, this was sort of the more complicated definition that I want to talk about today. But we also had the other major definition we talked about is what it means for a language to be regular. All right. So I'm just going to write that again. There's this one is not going to look crazy at all, really. It's more or less the same way that I wrote it before. But a language L is regular if there exists a DFA M such that L equals the language of M, right? That's what it means to be a regular language. Regular means that it is the language of some DFA. And like I said before, one of the major questions for the first big chunk of the course is just deciding which languages are regular and which are not regular. Anything you can do with the DFA is regular, and anything that you cannot do with the DFA is not regular. So the question of what is and is not regular is really the same question as asking what exactly is a DFA capable of, and what kinds of things is a DFA not capable of doing. All right? Great. We got about 10 minutes left. Maybe we can do a little introduction to the next sort of thing that I want to talk about. I would like to talk about properties of regular languages on the general theme of which languages are or are not regular. I'll say we've seen several examples of regular languages already. You know, just any example that we've seen using a DFA will be an example of a regular language. So things like strings on A's and B's where the number of A's is even, or where the number of A's is divisible by 3, or strings on zeros and ones, which represent binary numbers that are divisible by 3. That was a kind of a complicated idea, at least, although the DFA ended up being not so complicated once we figured it out. We've seen several examples of regular languages. I would like to know, is there some way of like combining regular languages together and getting more regular languages? So can we maybe build other regular languages from ones we already know? For example, I'm trying to ask a question like, for example, if, say, L1 and L2 are regular. Remember, a regular language just means a language is just a set of strings. A regular language is a set of strings which are the ones which are accepted by some DFA. If we have two languages which we know are regular, then I could ask, is, say, L1 union L2 regular? These are sets so that you can combine them in various ways. You could also ask, or L1 intersect L2 regular, right? If I already have some regular languages, what happens if I try to mix them together in various ordinary ways using set theory, right? Or you could ask about L1 minus L2. This is the difference of two sets. This means all the things which are in L1 but not in L2. Or even something like L1 bar. We're going to use bar to mean complement. The complement of a set, I hope you remember what that is. That's just the things, all the things which are not in that set, right? Is that a regular language? These are these basic ideas here. These are called closure properties. For example, it is a fact. I will tell you these questions here, I asked them as yes or no questions. Actually, the answer is yes to all of these questions. And we're gonna discuss this in more detail. But for example, this is a true statement. If L1 and L2 are regular, then L1 union L2 is regular. It's a fact. This is referred to, you can say this sort of, the slogan version of this is that regular languages are closed under union. I'm using this phrase in the way that you probably heard this used in algebra class or in linear algebra specifically, like this closed under business. You know, in linear algebra you talk about something being closed under addition, closed under scalar multiplication, that kind of thing. Closed under, it always means if you combine two things of this type, then the result is also of the same type. And we're talking about regular languages here. Regular languages are closed under union. It means if you have two regulars and you union them, the answer is still regular, all right? And then all of these other things, you know, so I want to talk about closed under unions, also closed under intersections, closed under subtractions, closed under complements, right? These are, you know, there's a whole section in our book about closure properties for regular languages, and that's the next big topic. We got time, actually, to discuss the simplest one of these is complements. Let's talk about complements. Regular languages are closed under complements. I want to see if I can convince us. I'll write this as a theorem. It just is going to say if L is a regular language, then L bar, the complement of L, is also regular. If L is regular, then L bar is regular. All right. I would like to write a kind of a formal proof of this, but maybe we'll leave that the formal version for next time. I think the basic idea of the proof is very easy. You have to imagine you have a language. Sorry, did I go off? No. You have a language which you know to be regular, and you would like to know if the complement is also regular. In terms of machines, it means that there is a DFA for L, and you want to know, is there a DFA for L complement? That is just all the strings which are not in L. So, for example, let's say I have a DFA already. How about just the one we had on the quiz again? All right. Let's say this is M. All right. This is a DFA which I'm going to call M. So, as you said on the quiz, L of M is all strings with some B in them, right? The complement would be, I suppose, all strings without some B in them, right? That's the opposite of this. That's what the complement means. It turns out there's a very simple way to take this DFA, change it around slightly so that it accepts only the opposite. Like whatever this one accepts, your modified one will reject, and whatever this one rejects, your modified one will accept. Anyone want to say it just in words? You can just say, how would you modify this picture to make it do the opposite, accept the opposite set of strings?
Switch the accepting state.
Yeah, we can just swap the accepting and rejecting states. And this isn't just for this example. Will always be possible to do this for any DFA, no matter how complicated it is. You swap the accepting and rejecting. You leave all the arrows the same. So this time, this one will be accepting, and this one will be rejecting. And I'm just going to say now, L of, if I call this one, let's call this N, just because N comes after M. L of N is L of M, the complement, right? This one will accept the opposite of the things which were accepted in the first one. All right. By swapping the accepting versus the rejecting states. So the moral of the story is, if you have a DFA which accepts something, you can always make a DFA which accepts the opposite. And that is to say that if you have a language which is regular, then its complement is also regular, because you can make a DFA to accept the complement. All right. This constitutes sort of a proof of that theorem that I wrote a moment ago. But next time I want to do just the same basic argument, but using set theory notation. And you will see actually it works out pretty easily, although it looks a little crazy because all that stuff be slightly crazy. All right. And I think I will leave it at that. So we got another homework assignment, which will be due on Wednesday. You will find it at our website. I haven't posted it yet, but I will, within a couple hours. All right. I hope you all have a great weekend.